In this video, I'm going to talk about how to visualize the simulation process. We still use the example of pendulum, but in this example, the reference direction is defined different from the reference direction we defined in the class. Here, the reference direction is the clockwise direction. In the class, we define the reference direction as a counterclockwise direction. Then by using Newton's law, you can get the equation of motion. As you notice that this equation, it is a nonlinear equation because of sine theta. Then you know how to approximate the nonlinear term by a linear term. We call it linearization. We can approximate sine theta by theta. Then the equation of motion becomes a linear equation. Then we can apply Laplace transform to get a transfer function. Here it is a typo. Theta s should be in the numerator, and Ts is the denominator. There will be output input because theta s is output and Ts is the input. You may see that we have the same transfer function, even though the reference direction is defined different from the example we used in the class. But it doesn't matter. So the reference direction doesn't matter. You can define either clockwise direction or counterclockwise direction, but you have the same transfer function. Then you can assign values for the m, the mass. You can assign any values, or you can also adjust the value by increase or decreasing. Also, the length of the rod, you can increase the length or decrease. Gravity force. Then initial positions. You can assume here is zero initial position, or how many degrees. Then we can simulate this process. To simulate the process, we need to define an input. So here we use the impulse input. The initial torque is 1 Newton meter. The impulse time is 1 second because we apply this torque only for 1 second. Then when we hit run, you will see the simulation result. You see here the impulse force, actually it is torque. This green curve is a line, it's an impulse. Look at the axis and the right, it is 1 for 1 second. Then it became 0 afterwards. The blue curve is the angle of the pendulum using the nonlinear model. That's a true model. And the red curve is the linear model we use to approximate the nonlinear model. As you can see clearly, the approximation is not very good. Then here it visualizes the pendulum angle. starting from 0 degree, then you can use the left and right button to apply the torque to the hinge of the pendulum. To the hinge here, you go left, you see the degree of the angle increases. See, if I apply a left torque, the degree increases. See the motion of the ball. Similarly, we can apply the right torque to the hinge. See the change of the angle. Then we can use the parameter we used in the book. I set M is 1, length is 1 meter. Then we can stop here and rerun the simulation. In this case, if you see the approximation is very good, we still use the same torque, but the linear model and nonlinear model from the simulation result, we can see they are almost the same. Then we say it is a good approximation. We can use this linear model for the control design. When the mass of the ball is large, but when the mass of the ball is light, the ball is light, we cannot use the linear model. A few parameters will affect the effectiveness of the linearization process. Then you see when the ball is heavy, it's not easy to make the ball move. See, I apply this torque, but I hold left, it is like a step signal. But the rotational angle is very small. When the rotational angle is very small, we can approximate the nonlinear function sin theta by theta. But the approximation is really bad when the angle is large. So the principle is we can approximate sin theta by theta only when the angle is small.